Good afternoon. Can everybody hear me? My name is Jason Lowe, and I have Arunava here as well. I'm from industrial engineering, and Arunava is from ECE. We're going to go through a short slide presentation today. This is not a sales pitch by any means, but it's just to give you an introduction to the world of collaborative robots, and we're using this particular robot, which is a Baxter by Rethink Robotics up in Boston, as kind of a case study that we've been working with over the past year and a half. So a little bit about my background. Why does an industrial engineer have a robot? Well, because of industrial, that word industrial. We have robots in our curriculum. We do a lot of automation in our curriculum. We have a manufacturing core that's part of industrial engineering across the way. And one of those aspects of automation is robotics. And we discovered Rethink, and we discovered Baxter about 2 years ago when it was a somewhat young company. And I can talk more about that as we go through the presentation. But just this is the platform that we're going to be kind of concentrating on in this particular talk. So what we're going to talk about in the next few minutes is what are industrial robots and how they evolved, Baxter in particular, some of the unique things about Baxter that make it kind of outside the norm of an industrial robot. Some different configurations. There's actually 2 configurations of Baxter that are available to the public and to universities. And how do we communicate with Baxter? This is a project that Arunava's we worked on last year with some other students that we put together for a high school curriculum that we had in our department. And then he's going to talk a little bit about the use of Baxter in research and some of the limitations that we are experiencing with Baxter and a lot of other collaborative robots that are available. So I may not be talking to the right crowd, giving you a history lesson about robots, but nonetheless, it's interesting for our ISO standard that a robot is 3 or more axes. So if you look back in the history books, robots used to be considered 2 or more axes. So if we go back to the 70s and 80s, there were a bunch of robots out there that existed, and a lot of them were just 2 axis configurations, but nonetheless they were robots. So today we consider a robot something a little bit different, or look at it a little bit differently. And in this instance, in this configuration, this is 2 7-arm axes, or 15-axis robot. And a lot of these industrial robots are either 6-axis or 7-axis types of robot. The advent of this collaborative robot that we're trying to get our minds around, and industry more so, is something that is to be working with a human or alongside a human. So in the areas that perhaps a lot of you are familiar with that lend themselves to autonomous vehicles, autonomous robots, service robots, and etc., that has been around for a number of years. In the industrial space, that hasn't been the case. In the industrial space, a robot was an industrial robot, and it was caged, and nobody interfered with that robot while it was working. In the present day, we're going to see more and more instances of robots working in tandem with people, working alongside people to do tasks more efficiently and making an environment that is much more flexible. So robots have obviously been around for many years, more than half a century. And this is kind of some of the evolution of robots over the years. And this really is a typical configuration. This one and the KUKA are relatively standard configurations that you would see in the industrial space. And then we kind of go into more or less ancient history with robotics over on the far right. So with Baxter, like I said, this is a 14 degree of freedom, or 7 per arm. It has a stature that is remarkably close to a human for basically an average size male, or maybe a little bit above average. So the intent here is to perhaps make this more approachable. As you can see that it is configured to be much like our human body in its form. It runs off of a standard PC. There is nothing unique about what's behind the scenes. It does run Linux, and it is a Dell PC. So I'm not really giving anything away by saying that it is just a standard Dell PC that you can go buy on the internet today. It has a camera. It has actually 3 cameras that we'll just briefly discuss in a moment. And one of the other unique things about it is there aren't very many industrial robots that you can just plug into the wall. So this is one that, as you can tell, we just wheel it in, and if we had enough time, we could go through a quick calibration and it would be up and running. So it's on wheels, it has stabilizers, but it is meant to move around and plug into any wall outlet. It does, on top of Linux, it uses, and Arunava is going to talk about this more when he discusses ROS. So it is built on a Unix kernel. The manufacturing Baxter, the one that you see here, has more of a wrapped application around it, and we'll talk about that in a few minutes. And as industrial robots go, where do we use them? Why do industrial engineers like robots? Well, we like robots because they're basically going to take things that are dull, dirty, and dangerous away from the human. In this case, with the Baxter, we have to be careful what we can do with that robot. It is not a high payload robot, it is not a fast robot, it is not a very highly repeatable robot, as we've come to find out. But it can be used in a lot of instances like kitting and packaging, machine tendon operations, and if you were to scour the web, that's where you would find these robots in these types of applications. This doesn't look so clear, but it has a considerable wingspan, given that it is a dual-arm robot, over 2.5 meters in its span here. So it has quite a work envelope that it can work in. And like a typical industrial arm, it basically follows a kidney-shaped sphere in its work envelope. A little bit about the sensing abilities of the robot. It has infrared sensors on its cuff, or on its wrist, and I can show you that. So at the tool plate, we basically, or where we would mount these grippers, we see that there are two sensors. There's a camera and there is an infrared sensor on each arm. So the other arm has the same thing, and then there's also a camera on the screen as well. There's 12 ultrasonic sensors in its crown, and these basically capture cloud data. So each one would give you a X, Y, Z point in space. And what is that for? It's basically for safety. So the robot can sense when there is something approaching, and it can either slow down or stop accordingly. These are in this version of the Baxter. This is kind of a unique thing in the design of this, is that there were more sensors and things that were put into the device prior to it having a maturity as far as its software or its applications go. So a lot of these things that we've discovered is that the ultrasonics in the crown or in the head are disabled. These are actually in the manufacturing Baxter, they're disabled, but we can use them in the research Baxter. And the camera on the LCD in the front on this tablet-looking face is also disabled. So when they designed this, and this goes back, this was launched in 2012, and they put a lot of work into it to get it shippable and get out there into the marketplace. So there were things in there that were a little premature, but they included them anyhow, and they're all active. It's just that some things aren't active in the manufacturing version of the robot itself. And I've talked about the cameras as well. When we talk about collaborative robotics, we have to talk about the style in which these control systems are designed. This particular robot is built upon what's called a series elastic actuator, and this was born out of Rodney Brooks's effort at MIT, and he started this company. He started iRobot as well. And they have basically the IP on all of this technology. But this is how this particular robot is able to be safe, be inherently safe, is through this series elastic actuator. So there's active force and torque monitoring, and they use a very unique horseshoe type of structure inside each of the joints, where they are monitoring the forces that could be by incidental contact be experienced by the robot, and they're able to react accordingly. So when the robot is running and it is moving around, it does meet the threshold of human pain, or pain threshold that is acceptable, and it will stop. This isn't a high-speed robot by any means, so when we look at industrial robotics, we're looking at meters or maybe 1 or 2 meters per second in their rapid moves. This is about 1/4 of that in its rapid move. So it's a very slow robot, and this is really how this is effective. They slow the robot down enough so they can do this relatively real-time monitoring of each of the joints and the actuators, and react in near real time. Yes?
So I've worked with industrial robots, and we've had to cage them, like you said in your initial presentation, with light curtains or even safety mats around that would shut all the actuator powers down if somebody approached the work site. And I heard the presentation at IEEE that was given on the Baxter robot earlier this year. And I was still wondering, do you consider this safety software interlocked or hardware interlocked? Because at the time, the safety people wouldn't let us do anything where software was in charge of the safety of the robot not harming or killing somebody.
Yes. So the standard, which I believe has a 2012 stamp on it, but it was recently enacted last fall, ISO 10218, addresses this in particular. And so there was a technical committee, an ISO TR 5016 or something like that, where they actually looked at the relative forces on each of the axes. If we look at a 7-axis robot, they did an extensive study, and it's still there's still work to do, and I think they'll readily admit that. But basically, what are the thresholds? So so the thresholds are one thing, but then there's the application itself. And that's what industry will always, I think, use as a good counter-argument, is that, if we're taking a rubber ball at this gripper and we're moving it around, maybe it's a 5-pound rubber ball, but given the speed and its reaction time, basically any part of the body that rubber ball hits, we're fine. But once we put a dagger in the hands of Baxter, then it's a weapon that would basically violate all of those thresholds.
Or if Baxter could do a crushing motion or something, even if it isn't a sharp weapon, you can imagine Baxter doing something. If it were under improper software control, it could use the force of lifting to apply enough force to hurt somebody.
So that is a very active discussion.
Okay.
I can tell you that, and they are allowing these to go cageless. And right now, I don't think you can purchase any collaborative robot that is over 10 kgs, that has more than a 10 kg load limitation. I think until the standards are further developed, that's probably in the space where it's going to remain, is at these very low payloads and relatively low speeds. Yes, are we going to see this being a welding robot? Probably not in the near future. But as I mentioned, the typical material handling types of applications, it's well suited for. Many parts are under those 10 kg limits anyhow. So it's a good point, and I think other robotics companies are finding other unique ways of dealing with this outside of Baxter's or Rethink's attempt at using these series elastic actuators. But it is an active discussion that there's 2 big robotic safety conferences every year, and I try to get to one of them each year. Thank you. I hope that sheds a little bit of light.
That's a very elaborate answer, and I appreciate that, because as a software engineer, I spent a lot of time arguing intrinsic safety of software systems, and the safety engineers at IBM would say, no, we don't trust software, got to be hardware interlocked,
And the controls people will always stay with the hardware answer.
yes.
Yeah, so at the safety conferences that I attend, there is this overarching feeling that there's the controls people that are hardware people at heart are really arguing that it has to be a hardware control.
Yeah, I'm not exactly sure, since I've seen a lot of hardware malfunctions as well, why hardware engineers and safety engineers trust hardware over software, because it fails too.
And to the software debate, so in a typical industrial setting where you've got a robot, whether it be collaborative, in this case this one doesn't have it, but you would have a teach pendant. So up until now, you had to have this umbilical cord from your teach pendant to the system, to the control system. So that is its own area of discussion, because now that's both hardware and software. We're crossing the boundaries there when we want to make it wireless. So that is a big area and there is a company that's doing that, not in the United States. I think if they were, at this point, if they were to try to bring those in, they'd have a difficult time with some of our rules and regulations. Oh. Okay, I'm just going to speed along so Arunava can have a couple of moments here. Pardon? I don't want to take anything away from Seth, so let me just speed through this.
We're on last.
So last summer, very quickly, communication side of the picture. How do we communicate with these robots? With the industrial Ethernet standards and things have come a long way. So we're doing more and more with Ethernet, but there are a lot of legacy systems. RS-232 is still out there that we have to use. This particular unit will use Modbus. So we can use a variation of our Ethernet to do communications. So one of the things that I was going to show you, and I'll make that public, is a video that we had a case study on last summer, where we had robots talk to each other and worked in coordination with each other using Modbus. So that was kind of the point here. Now I'm going to let Arunava talk a little bit about the research side.
You can hear me? Okay. Jason went to this manufacturing robot over here, so I'm just gonna give a quick slide. I'm not gonna describe so much on this what's actually the ROS or the research robot, because given the time. So I'm just gonna throw some information that is this robot comes with a second configuration which is used for research purpose, and it has a ROS framework inside it. And you have a lot of flexibility in that, because in this system, which is just a manufacturing, it has only you have a software built on it, and you can only use the features given by the software. Like here, you can pretty much build your own software and get it to work, and also control your force, torques, or whichever way you want to use it. So it can be also simulated, and there are tools like Zibo and Moveit, and also visualization of the result is possible through Arvis. These are the basic tools given in the ROS. And if this slide is being made public, we have hyperlinks over there which can actually give you an introduction to what are these things. So this is again what we can actually use Baxter for. Some of the very hot topics of research are, one is the vision system. So pairing it with a vision system to get it to work and do some kind of robot manipulation. That would actually also take out the training and teaching phase, and it will be completely autonomous on the assembly line. Next is again choice of a camera is also research, because Cognex is one of the machine vision, like leading vision. However, it's pretty expensive. Next, this is also good for, like, we know that robot is all about like intelligent learning and artificial intelligence algorithms. So this can be used for learning purpose. There was a recent competition for the Rethink Robotics worldwide, and the first winner did actually like object sorting and learning. So it gets like a bunch of objects over there, and it kind of sorted out the object of interest and left behind the things which are not relevant. So that kind of algorithm and intelligence can be built using this, and human-robot collaboration is definitely possible. Some of the limitation, Baxter recalibration, the arms continuously try to recalibrate itself, and that's why it doesn't have a, I won't say like it doesn't have proper stability. Sometimes it shakes, and it has a offset of maybe like around 0.2 millimeters or something, and it's slow. Jason already mentioned that it's not as fast as Motorman and other industrial robot. Yeah, I think it's kind of a trade-off between safety and use applications. Some of the adoption is it's open source, and that makes it like interesting for the research communities throughout the world, and that also brings new minds to work on and bring more intelligence to this machine. And yeah, so I'll just say something about the research we are working on at this point. This is a shot from the last summer where Jason, myself, and Ishmael, the other gentleman on the left, has actually worked on it. So the research at this point, what we are working on is having this robot to work in the assembly line and automatically recognize the object in which has been which should be handed off by an worker, and should be able to manipulate it by itself. There shouldn't be any training phase. All it needs is a reference model for recognizing the object. We are using a paired vision using a Kinect for 3D vision, and the Kinect basically gives us a point cloud and the 3D information of the object which is present in the field of view, and that is basically we are using disparate source of data together to enhance the automation and even like taking out the automation phase, like the training phase. Yes, sir. Are you asking? I'm sorry. Yeah. Yeah, that should be it. Any questions? Yes. You mean the price?
Yeah. Baxter, I believe the last listed price was $24,000, and that is from its midsection up. They charge you for the base. Not everybody wants to mount the robot so it's mobile, so they do sell just the bare bones torso, and then you buy the grippers separately as well. And they've had their own market for the grippers, but now they're opening that up so others can use their software to configure their own custom grippers.
The 3D space modeling is can you describe the representation model for 3D space in your software and how you interact with it? Is it vector? Is it Cartesian? Is it?
It's Cartesian XYZ data. And Arunava can speak more.
So basically, when we get the data from the camera, that is 6 degrees of Cartesian coordinates.
Okay.
When you feed it to the inverse kinematics or the IK solver, it goes into 7 degrees of robot joint angles.
Okay.
Quick question. What's the XYZ accuracy? You said it was pretty poorly, or is it?
So there's no published accuracy.
Okay.
Robotics companies hate to do that because they're afraid you'll hold them to it. So the repeatability is more of the question with a robot. And when we first got the robot, so we're going back about 4 software revisions. This goes back about a year and a half. We were lucky to get about ½ a centimeter repeatability, but now we're down to the millimeter range at least, maybe 2 to 3 millimeters repeatability in its work envelope, which is pretty good. But again, that's at very
Another question. I know you guys work a lot with the Baxter. Was there any kind of possible collaboration with robotic surgery?
That's a good point. I don't know if I'd want, even if I were an animal, I don't know if I'd want Baxter operating on it. But yeah, that's a very good point. There's at least 2 or 3 places in the triangle that are developing surgical robots. So and collaborative is part of that.
Do you design your work cell apparatus for compliance so that Baxter can, fit something and it gets, wiggle it in and things like that?
Yes.
Okay.
So jigs are an important part of the equation. Having proper jigs that can do the alignment are a big part of it. And what we'll do is we'll give the video to Charlie to post because we are out of time, and thank you, Steph, for letting us go over. And if there's anybody that wants to talk offline, it's jclow at ncsu.edu.
Finish the video.
We're going to post the video.
You can go ahead and play it while I'm waiting.